Hi everyone, my name is Ofe Desmond Delali, and I'm here to do a presentation on the summary of an energy model for visual graph clustering by Andreas Noack. Now, let's start with of an intro to graphs and energy models. So a graph, which is given by the function g equals VE, is just basically made up of a finite set of nodes V and a finite set of edges E. Note, for the purposes of this article, the writer used only graphs with at least two nodes for their research purposes. So what are energy models? So energy models are commonly used to show clusters for a graph or to create drawings from which a human viewer can infer properties of the graph drawn. Okay. Now let's go to the problem statement. So what is the research paper trying to tackle? So the problem the research paper aims to address is that the drawings of most energy models do not clearly show clusters for graphs whose diameter is small relative to the number of nodes. Now, what's a cluster? So a cluster basically refers to nodes grouped together based on some common characteristics. Okay. So now let's move on to the objectives of this paper. So the main objective of the research paper was that the paper aims to introduce an energy model whose minimum energy drawing clearly reveals the clusters of such graphs identified in the problem statement. That's graphs whose diameter is small relative to the number of nodes. Then secondly, the writer formally characterizes the minimum energy drawings of his or her energy model. This characterization was done so that this characterization shows in what sense the drawings separate clusters and how the distance of separated clusters to the other nodes can be interpreted. So that was why the writer implicitly stated the formal characterization of their model. Okay, so this was the model introduced by the writer of this article. So the name of the model is the Linlog energy model. So the Linlog energy model, which we normally represent by U, lower subscript Linlog of P, of a drawing P is defined as follows. So basically the summation of the norm of PU minus PV minus the summation of the lane of PU minus PV. Now the first term PU can be interpreted as the attraction between adjacent nodes. So basically the attraction between nodes that are adjacent to each other. And the second term PV can be interpreted as the repulsion between any two different nodes. So the repulsion between two different nodes is the PV, and the attraction between adjacent nodes is the P of U. Now the underlying assumption for this model introduced was that the writers assumed that the different nodes have different positions. So this was assumed to avoid infinite energies. Okay. Now, how does this model work? So this model introduced, the Linlog energy model, works by minimizing the ratio of the average edge length to the average distance of all pairs of different nodes. So this model works by minimizing the ratio of the average edge length to the average distance of nodes. Okay. So let's show. So this is how the Linlog energy model clearly works. So we can see clearly the drawing. So basically this figure 1 shows it's used to demonstrate the power or the effect of the log energy model. Figure 1 here shows the drawings of a pseudo-random graph with clusters for the log energy model. So the log energy model is on the left, and another famous energy model, which is known as the Fuchs-Reingold model, is on the right. It can be clearly seen that the log model on the left clearly reveals clusters compared to the other model on the right. So the left model, which is the log model on the left, which clearly reveals the clusters, we focus on. So we can see that the log shows a graph with 4 clusters, each having 4 subclusters of 50 nodes. The drawing for the log model clearly shows the hierarchical structure as well. So basically, the log model has been able to achieve what the writer wanted to show, which is clearly showing clusters, which is being shown here. Okay. So in conclusion, the log energy model was introduced by the writer of this paper as a better choice for graphs whose diameter is small relative to the number of nodes. Okay, so in these drawings, this was shown on the previous slide, clusters are clearly separated from the remote nodes and they are distant. So then we can conclude that indeed the log energy model is a better choice for revealing clusters clearly where the diameter is small relative to the number of nodes. And that was the whole point of this research paper. So that was what the research paper wanted to show. Thank you.